Okay, so let's start with the new topic, VLSI design styles. All right. Look at this diagram. This is showing different types of VLSI design styles that are commonly practiced. So we have full custom, then mm, just a minute. Yes, then we have cell-based or standard cells design style. That this comes under this semi-custom VLSI design styles. So basically, we are having three major types of VLSI design styles. That is full custom, semi-custom, and programmable array. Sorry, programmable. Okay. Under semi-custom, we are having two types: standard cells and masked gate array. And then under programmable section, we are having FPGA field programmable gate arrays, then CPLD complex programmable logic devices, and then PLD programmable logic devices. So we will see each one of these, that what are the differences and how are they, where are they used, in what situations are they used. Okay, we will see each of these. Okay, so let's start with the mm, first design style, that is the full custom design style. Okay, so full custom design style is one of the oldest and the most traditional technique that is used for designing VLSI chips. And as the name suggests that the name suggests full custom design style. It suggests that everything will be built from scratch. Okay, that everything is built from scratch. So there is, what is the starting point? The starting point is zero. Okay, all the thing has to be built from the very initial from the very initial phase. Okay, nothing is available for uh, reuse and you know these kind of things. Okay, so uh, one thing that the mask. Okay, the mask plays a very important role in fabrication of VLSI chips. Okay, so everything that refers to the design of VLSI chips will also be referring to uh, the fabrication of or the designing of masks. Okay, in some cases, especially in FPGAs kind of things where programming is used and FPGA hardware is already available, we may not be requiring the fabrication of mask. But in other cases, mask fabrication would be essential. Without mask, various ICs cannot be fabricated. So especially in this full custom design style, when it comes to the fabrication of mask, okay, then how would it be designed? So it is already known that everything is built from the scratch. Okay, so the entire designing process of mask is done again from the scratch, and without the use of any library. Without the use of any library, there is no availability of any sort of library components and those things that can be reused uh, to make the design process easy. No. So this full custom design style itself says that uh, the full uh, the full complete flow has to be followed. Everything has to be designed from the initial phase, and then it should be used to fabricate the VLSI ICs. Okay, so like it doesn't have the uh, availability of library also. So even the library components also needs to be designed, and then those components will be used for fabricating the ICs. You know, so this is a huge task. You have to build first a library, fill it up with the different types of components that would be required in that particular IC, and then use that library components to you know fabricate or to produce the required particular VLSI IC. Okay, so it automatically it will incur a very prohibitively high amount of development cost. The development cost is very high because everything has to be built from scratch. Okay, so if the cost is very high, then there's always a trade-off. Okay, there is no such technology which will give you all kinds of benefits. Okay, if there are some benefits, there will be some down points. If there are some advantages, there will be some disadvantages. Okay, so here one of the most important disadvantage is that the development cost is very high, very high. Okay, in fact, this kind of VLSI design style incurs the highest amount of development cost. Okay, so if it is giving us a very high amount of development cost, then what is the use of this VLSI design style? Huh? So the use is this: since all the components, all the things are built from scratch, from the zero, from the very initial phase, so we have full control on the performance of each of those components. It means that each of those components that are designed from the very initial phase, we can optimize those components according to our need. Okay, okay, so we can optimize those components according to our need according to our requirement, and hence the IC that will come out after this phase will be the most optimized IC we can fabricate, we can achieve among all of these uh, VLSI design styles. Okay, okay, be it semi-custom or programmable. Okay, so this is one point, that although full custom design style is a very costly affair, okay, but it will give us the most highly optimized VLSI chip that any other design style cannot give. Okay, so this is the advantage. So they, on one side we have a very high cost, and other side we have a fully optimized ICs that can be fabricated. So what is the use? So where can it be applied? Okay, so the thing is that if somehow we can reduce that development cost, we can bring down that development cost. Is it possible? Okay, so what can be done? So because of this, full custom design is limited to ICs that are to be fabricated in extremely high volumes. Okay, so it is particularly suitable for those kind of ICs which are to be fabricated in millions and millions and millions of numbers. Okay, for example, microprocessors, they know that the companies know that the microprocessor chips will be sold in millions. Okay, like every laptop, every desktop contains a microprocessor, and now almost every student, every professional has got at least one laptop. Okay, so there is a huge market for laptops, and hence there is a huge market for microprocessor, and it will sell in millions. So this particular microprocessor IC is fabricated by using this full custom design style methodology, or design style. Okay, so wherever the requirement of the IC is very huge, in that case the full custom design style can be used for fabricating that particular IC, uh, to bring down the cost, to bring down the development cost. Okay, so in real full custom layout, in which the geometry, orientation and placement of every transistor is done individually by the designer, design productivity is usually very low, typically a few tens of transistors per day per designer. Because everything has to be done from the very starting phase, so it takes it takes sufficiently high amount of time to complete the process, and also the productivity is very low. because everything has to be done from the very scratch. So the productivity is typically a few tens of transistors per day per designer. Okay, so this was about full custom design style. So remember the points that this is one of the oldest technique, and this requires everything to be built from scratch, and hence, since there is no availability of any library as such, so the development cost is very high, comes out to be very high for this particular design style, and hence this is suited for those kind of ICs which are required in millions of numbers. Okay, so next comes this standard cell based design. Look at this, it will come under the semi-custom VLSI design style category. uh, this standard cells based design, or simply cell based design style it is also called. Okay, but this standard cell based design, this term is more popular. So what happens here, what it separates from the full custom design style is that, so there is an availability of library in this case. Okay, no doubt that there was no any such library present in full custom design style, but here a library is present. Okay, and that library will contain different types of components that may be required for any kind of IC designing process. Okay, so this shows a typical standard cell library that will contain these kind of components. So it will contain inverters, buffers, tri-state buffers, NAND, AND gates, NOR, OR gates, XOR, XNOR gates, and or invert. OAI is OR and invert. These are complex gates. Different kinds of multiplexers, adders, latches, flip flops, and input output pads, IO pads. Okay, and moreover, these different kinds of components will be available in different flavors, different sizes. Okay, for example, for the case of inverters, let's say inverters. Okay, it will be available with wide range of power options like 1x, 2x, 4x, 8x, 16, 32, 64 times. X means times, 64 times minimum size inverter. So there will be a one inverter that will be of minimum size. Okay, and these 1 times, 2 times, 4 times means 4 times means 4 times the size of that minimum sized inverter. Okay, so if there is one minimum size inverter, then we can expect that a 2x inverter uh, will have almost double the power driving capability as that of that minimum sized transistor. Okay, and it also says that this 2x will be having a fan out of uh, double the fan out as compared to the minimum size inverter. So let's say if this is an inverter, okay, one input and one output. So if I say that this particular inverter can drive only one inverter at its output side like this, then in this case, what is the fan out for this particular inverter? The fan out is 1. How do we calculate fan out? Fan out is the number of components that it can drive at its output side. Okay, if I say that it can drive only one particular component at its output side, the fan out will be 1 here in this case, if this is the minimum size inverter. Okay, now talking about this 2x inverter, we I can say that our 2x inverter will be an inverter which is having twice the capability of this minimum size inverter. So it is able it is capable of driving two inverters at its output side. Okay, this is the first inverter that it can drive, and this is the second inverter that it can drive. Okay, and this is the 2x times the minimum size inverter. So the capability in terms of driving the number of components at its output size is double. So it can handle twice the amount of power, and it can handle twice the amount of output load traffic as compared to this minimum size inverters. And hence 4x inverter will be four times the capability as compared to the minimum size inverter. And similar will be the case for 8x, means 8 times, 16x 16 times, and so on. Okay, and let's look this NAND and AND gate uh, can be available in terms of different number of inputs. Minimum input required is 2, so we can have 2 input NAND gates, we can have 4 input NAND gates, we can have 8 input NAND gates available in the library. Okay, and all of these different kinds of NAND or AND gates would be available again in high, normal, or low power options. Okay, again it means that they will also be available in terms of like 1x 2x 4x 8x 16 times the minimum sized AND gate, or the minimum sized NAND gate. Okay, and hence this will be true for all other types of components also, like NOR or OR gate, again with varying types of inputs in high, normal, or low power flavors. And similarly it will be applicable for almost these kind of components also. Okay, so it uses a standard library as the basic building blocks of a chip. So the library is available here. There will be a library that we call this as a standard cell library that will contain the components would be used for fabricating, for building a particular chip. Okay, so in this design style, all the commonly used logic cells are developed, characterized, and stored in a standard cell library. And from that standard cell library, you pick up the components, connect those components, and then fabricate uh, the required IC. A typical library may contain a few hundred cells, including inverters, NAND gates, NOR gates, complex AOI, OAI gates, D latches, and flip-flops, and so on. Okay. So what is the difference here that differentiate this standard cell-based design from full custom design is that the library will be available for the designer. Okay, and mind it, the availability of library or the availability of the components is a huge relief for the designer, so that he has the freedom to pick up any component that he may want to incorporate in his design of IC. Okay, so it means that the turnaround time for designing IC would automatically reduce. The time required for designing IC will get reduced significantly. The cost will also get reduced significantly. Okay, but what about the performance? What do you think? The ICs that are fabricated using this standard cell-based design, what would be the performance of these ICs as compared to those ICs which are which are fabricated by using full custom design style? Okay, think about it. Uh, so cell-based design can deliver smaller, faster, and lower power chips than FPGAs. FPGAs will come later on, but has high NRE cost to produce the custom mask set. Okay, sorry. So it has high NRE. NRE is non recurring engineering cost. Okay, so the cost that is spent in the initial phase of the design and in the initial setup of the design, and which cannot be recovered. Okay, so it has a high NRE cost as compared to FPGA design style. Okay, because in FPGA the hardware is already available and we just do the programming. We will see. So still the cost is a bit high, but as compared to full custom design, the cost is not that high, and hence this is still suitable for high volumes of production, where high volumes, high numbers, a large number of production is anticipated. Okay, so this is a standard cell layout with some of the constraints, like every cell, remember, what did I tell, that what is a cell in that Y chart or Galski chart? A cell represents a cell may be representing a particular small component. It may be representing a transistor, a single transistor, okay, or a single small gate. So, and every cell, every small component will be having its layout, because it has to be ultimately fabricated on the IC, on an IC, okay, on a particular area. So it will have some it will have its unique kind of architecture or unique kind of layout. We say like this, the layout term we use. Okay, layout. So just look at this diagram. No, do not get fearful about after looking this. We will understand as the time progress. We will get to, you will get to know that what all these linings, all these, you know, dark spots, all these different layers means. Just but with a free mind, just look here that this portion is for the power supply VDD, okay, and this portion is for the ground, okay, and in between power supply and ground you have the main component. Okay, so okay, so this is generally the PMOS, P transistor area, okay, and this is the NMOS transistor area, right, and this one is the metal line that connects the P transistor area with the N transistor area. Okay, and there is a small, you know, here metal, this blue colored rectangles represent metals. Okay, so there is a small gap here, metal to metal spacing, right, and there is a small gap here also. This is metal to metal spacing. So this is VDD, this is ground, this is PMOS area, this is NMOS area, and this is the connecting metal between PMOS and NMOS, and this black colored rectangular line, this black colored rectangle is actually the polysilicon that connects again the PMOS with NMOS. So this is acting as the channel. This black colored stripped rectangle is acting as a channel between uh, 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 not channel exactly, acting as a, you know, connection, acting as a connection, connecting wire between the P transistors and the N transistors, right. And here the this middle portion is used for feeding the input signal, and getting the output. Okay, so this is just one simple layout, one simple example of layout of one typical cell. Okay, so what are the main points that you have to remember? Okay, the structure will be like this for almost all types of cell. The structure will be like this: the power, the ground, the PMOS area, the NMOS area, and the interconnections. That's it. Okay. So the height of the cell is defined by the sum of NMOS and PMOS. If you if I say that calculate the height of this particular cell, that how much length it acquires from this point to this point. How would you calculate the summation of each of these components? This one, this one, this one, this one, this one, and this one, right? So the sum of NMOS and PMOS transistor width. Okay, this is PMOS transistor width, and this is NMOS transistor width, right? Okay. Then the separation on N and P regions. I think the separation on this separation it is talking about, this separation on P region and this separation on N regions. Okay. The spacing to VDD and ground buses, uh, and the width of these buses. I think the spacing. Okay, so this spacing is about this space and this space. So this the separation on N and P regions was I think this is the separation between P and N. So this particular separation between P and N represents this particular parameter. Okay, and the width of these buses, the width of the VDD and the width of the ground bus. So when you combine this particular space plus this plus this plus this plus this plus this plus this, you get the complete uh, height of this particular cell. And similarly, you can also calculate the width of this particular cell by adding, this parameter with this parameter, and you will get the the you will get uh, you will get the width for this uh, width for this cell also in this case. Okay. um, Forgive me for my drawing. The drawing is not that good, but you try to get the concept. Okay. So after chip logic design is done using standard cells from the library. The most challenging task is to place the individual cells into rows and interconnect them in a way that meets stringent design goals in circuit speed, chip area, and power consumption. Okay. So it says that after you pick up the components, so this, like say, this is one component that is picked up from the library. So you will pick up several components from the library, and then you will place these uh, components on the particular IC area, and you will interconnect those components by using interconnections. Okay, and overall this will be a very complex process, but what thing you should take care while designing a chip is that there would be some specification in terms of the circuit speed, area, and power consumptions. Okay, so anyhow you will have to meet the constraints that are laid on that at what speed the particular chip should operate, at what area it should consume, at what amount of power it should it should consume. So remember, in any particular IC design, the three most important parameters that are to be satisfied would be speed or delay. Okay, speed, area, and power. Right. Okay. So here, look at this diagram. Okay, this shows a simplified floor plan for of standard cell based design. Standard cell based design. Floor plan. So a floor plan will show us the arrangement of different components on this particular IC area. So let's say this complete, it shows the particular IC area. Okay, and inside this IC area, all the different types of components, all the different types of pins are to be arranged and connected. Okay, so here these are the standard cells that are placed along a row. Okay, here in this one line, and then some space is given for routing. So routing means for interconnection, for connecting these components with other components. Again, there would be a row for all standard cells. Again, some spacing is left for interconnecting wires. Again space, again components. Okay, So this is one design style under standard cell approach. Okay, and these the rectangles that are present along the boundary of this ICs, they are the IO pins that are available, that will be used for connecting the input and output signals, and will communicate with the external world. Okay, so this is one particular simple floor plan of standard cell based design, right? So this look at this. This is mask layout of a standard cell based chip. This is the actual mask layout. Okay, and this looks completely different from this particular simplified floor plan. Okay, so this is the actual mask layout that will be used, that is actually used for fabricating the ICs, right? uh, with a single block of cells and 3 memory banks. So okay, so this is the first memory bank, this is the second, and this is the third memory bank. Okay, this one complete is one memory bank. Memory bank are highly regular in structure, so they will look they are easy to identify on an IC chip area. Okay, and this particular area contains all the standard cells placed, and try to relate this particular area. Okay, try to relate this particular area uh, try to relate this particular area with this particular type of configuration. Now you can now you will be able to connect between this one and this particular diagram. Okay, so this was all about standard cell based design. So what are the features? That there will be a library. The library will contain certain amounts of certain number of different types of components, having different flavors, different sizes, and varying with different number of inputs, and having different kinds of output fan outs. Okay, and depending on the requirement of the design, designer will pick up any of these components and then place it on a particular chip area, and then will connect those components by using interconnections. Okay, and then we'll go for the mask generation, and after mask generation will the actual IC will be fabricated, right? Okay, so